Previously, when we've worked with the concept of absolute value, we've developed exactly what absolute value is in terms of its being the distance of a quantity from zero, and then we've also solved various equations and inequalities and represented those solution sets. But when we did so, we only had one variable involved. So we're going to step it up now and use two variables in absolute value equations here, and later on we'll also see two variable absolute value equations as well. So to be able to represent the solutions, it's really best to kind of make a picture, or in other words, represent this in two dimensions or in a coordinate plane. So before I actually do one inequality that's going to actually involve absolute value, I want to go to this right here and represent this relation, y equals x. And of course, if we make a table of values for this, it's a pretty simple table of values to make, because if the equation is just y equals x, then of course all of the x values are going to be the same as the y values. So when we represent this relationship in a coordinate plane, these will give us these ordered pairs here. Now, of course, we're not just restricted to just those 9 ordered pairs. We can have any of these other ordered pairs, because, you know, like negative 1.5 and negative 1.5 is going to show up on there everywhere, right? So it's just a diagonal line that's going to represent that particular relation there. So if we just make one small tweak and we have y equals now the absolute value of x, okay, and we treat x as the input, then what you actually get as corresponding outputs are a little bit different for part of this. So what we're going to see is that whenever we have a negative x input, we actually have a positive y output. But then similar to before, when we have a positive x input, we actually still have the same positive y output. So it does turn out that actually you're going to get a graph that really kind of has the shape of a letter V for this absolute value function that we're seeing here. So in terms of like similarities and differences between the two graphs that you see here, you're seeing that, of course, these aspects of the graph are actually identical to each other, but what we saw happen with this part of that line is it really kind of got reflected over the x-axis and became that part of the V right there, just basically because of the fact that an absolute value of a negative number is, of course, going to become positive. So what we're going to see is that when we deal with absolute value functions, they kind of form their own family of graphs that are going to kind of have a V shape. So the parent function of any family, of course, is the most basic function you can have in a family. And for the absolute value function family, y equals absolute value x is going to be that parent function, which we just graphed. And so it's going to be this V shape that's going to have basically kind of a line for that part of it that's got a slope of 1, and then another separate line there that's got a slope of -1 that extends infinitely there. A couple of terms to introduce about this V shape here. So that tip of the V right there, we denote that as the vertex of the graph, so it's a very important term you want to know. And then a second thing is if we were to, like, I don't know, take a scissors or something and cut along that dotted line that I just made right there, what that's going to do is it's really going to cut the graph in half so that you get a mirror image on both sides of that line. And so what we call that line right there is we often will call it a line of symmetry, because we do get symmetrical images on both sides of that line. Sometimes we may call it a line of reflection, or we might, instead of using the word line, use axis. We might say axis of symmetry or axis of reflection. And I wrote symmetrical there, and what I intended to write there, of course, is axis of symmetry, or line of symmetry there. So what we're going to just kind of do now is just look at various transformations that we can do to the equation y equals absolute value x, and we'll kind of see some patterns develop. So what I'm going to do first of all is I'm going to take y equals absolute value x and just make one small tweak, and the small tweak that I'm going to make here is I'm going to add some number k. So in the case of this equation, we're going to add the positive number 2, and then right there we're adding the number -3. It's technically subtracting. You can think about it that way if you want. And so based on, if I treat this column right here actually as absolute value x, we know that we're going to get these particular values right here. So then if I create now a third column to this table, and then I make this column actually be labeled with the absolute value of x, plus 2 is equal to y, really all that's going to do, right, is take the purple numbers and just add 2 to all of them. And so all that's really going to happen is these numbers that are going to be in this blue column are just going to be basically 2 higher for all of the y values, but then the x values all remain the same. So all that's really going to do then when I actually graph this is it really just shifts the graph up 2 units. And so we just get a V shape that's going to look like that, and that's going to be the graph of y equals absolute value x plus 2. So by a similar regard, of course, in the example just to the right of it, if you just subtract 3, it's just going to subtract 3 from all the y values, but the x values are all going to remain the same. So your V shape really is just going to shift completely down exactly 3 units and look something like that. And we can draw the arrows there to signify that it will go on forever in both directions there. So what we're seeing is that k, when we add it there, in comparison to the graph of y equals absolute value of x, what that k is doing is it's doing what we call a vertical translation of k units. So it moved k far, right? It moved positive 2 or it moved negative 3 far. But vertically, and vertically means up, down, right? And translation is kind of a geometric word, and what a translation is you just take some sort of object and you're just going to slide it around. So you're allowed to, move it up, move it to the right, move it down, move it left, okay? But you're not going to actually change the actual shape of the object itself. You're just moving it to a different position, up, down, left, right, that sort of thing. So that's what we're seeing there. So with the next sort of transformations that we need to be able to understand, I'm going to tweak the equation of y equals absolute value of x, but this time I'm going to actually do a little bit of number work inside the absolute value rather than outside of the absolute value of x. So what I'm going to do here is I'm going to actually subtract some number h. So what I want you to see is what happens when I subtract, in this case here, a 4. And then I kind of want you to think with this one right here that we could write this as y equals absolute value of x subtract negative 5 and treat it accordingly. And so a nice way to kind of get some intuition into this is really just to make a table of values. And so I'm going to start with this graph over here and make a table of values. And if you do plug in these x values, you will get the following corresponding y values, and I'm going to make the table even bigger. So I'm going to plug in a 5 and then plug in a 6, and you do end up getting those particular y values that correspond. So what we're going to actually see happen here then is we'll get the following ordered pairs, and then it starts to switch direction again, and you can predict, oh, it's another V shape, right? And that's exactly what's going to happen. Okay, it's just the V shape actually just got moved, but horizontally this time rather than vertically. And so that's exactly what's going to happen when we subtract or add some sort of value inside the absolute value with the x. Is it's just going to do a horizontal shift. So without really actually making the table of values for the next one, if you see that it's x plus 5 inside, so anytime you're adding inside, it's actually going to shift it the opposite direction of what we just did, which is to the left. So here when we saw that we were subtracting a positive 4, that's going to be a right shift by 4 units, and when it's adding, it's a left shift. So it's just the vertex of the graph shifts left 5 units, and then you can just go at a slope of 1 and then a slope of -1, kind of on both sides there to be able to construct the V-shaped graph that you're going to see there. So ultimately, this h, if we think about the h in the y equals absolute value of x minus h, and we compare it to y equals absolute value of x, this graph right here is just going to be a horizontal translation of what y equals absolute value of x is by exactly h particular units. Okay, and so we get a horizontal translation out of that. And then a couple more things to kind of think about in terms of affecting our graph of y equals absolute value of x. So side by side here, you can see these two examples. One has a 2 multiplying in front, and the other has a negative 7/2 multiplying in front. So what we're just examining right here is what the effect of multiplying the absolute value of x is going to have. And so if you just think about, if I had just the absolute value of x only, of course you're going to get these particular y values, and then I'll create, again, another third column that will then actually have 2 times the absolute value of x. And then what we're going to see is really just going to double those blue numbers that I have. So you're going to have 8 and 6 and 4, 2, 0, 2, 4, 6, 8, right? So really you're just kind of like doubling the y values for the same x values that you had. So if I do end up plotting this graph right here, we get a V shape, but it's going to be what I would describe as like if I were to hold my fists like this, and then I were to like hold a rubber band between my fists and then stretch vertically with that rubber band, right? What happens with that rubber band is kind of what's happening with the graph right here, because the graph of this V that we see here is like stretched vertically, right? And it's a little bit skinnier this way compared to if it was just y equals absolute value x. Because y equals absolute value x would be the graph of this gray V right here, okay, which is not as stretched vertically, right? It's a little bit wider horizontally. So what's happening is we are experiencing what we call a vertical stretch by a factor of 2. When we say a factor of 2, it's just being multiplied by 2, and we call it a vertical stretch just based on my description there of kind of that rubber band aspect pulling in a vertical sort of direction. So if we were to transition over to y equals negative 7/2, basically the same thing's going to happen, but what you're going to notice is that if you multiply by a negative, then if I make a column here first for just negative of the absolute value of x, you actually get all negative y values, well, except for that 0 right there would kind of be the only exception. But what that's going to do is really it's just going to flip your V shape, go upside down. And so what that's going to cause is what we call a reflection. So that negative does a reflection, and it reflects it in the x-axis. In other words, it reflects it over the x-axis when we say it reflects in the x-axis. But then there's another aspect we need to consider right here, which is this 7/2 aspect. And similar to what we saw with the 2, it's kind of just almost like the slope of this absolute value graph here. So it's going to go upside down, but then what we're going to see is that it's really going to kind of go at a slope of negative 7/2, like you're kind of seeing occur right there. So it does become a little bit skinnier. It did get stretched there as well. However, when we get numbers that are like these couple of numbers here, we're not going to see a stretch because these particular numbers, 0.6 and negative 1/3, when you absolute value them, they're going to have values that are smaller than 1. And so it's actually not going to stretch the graph. It's actually going to make the graph grow less vertically. So it's actually going to be kind of like you're pushing into the graph, making it grow less and kind of going flatter like a pancake. So a good way to think about this first equation right here, the y equals 0.6x, is also to think about it as y equals 3/5 times the absolute value of x, because 0.6 is the same as the number 3/5. And so if you just go at a slope of 3/5, in both directions, or negative 3/5, I guess, in this direction right here, that's going to be the graph of y equals 0.6 absolute value x. It is a little bit more flat compared to just y equals absolute value x. So what we see occurring here is we do see what we call a vertical compression, not a vertical stretch, because we're vertically pushing in on the graph and making it flatter. So it's a vertical compression, and then we still use the same terminology by a factor of whatever the factor might be. So in the first graph at the left there would be 0.6, and then in the next one would be by the 1/3. Of course, because it's actually a negative, it's going to make it go upside down, but you'll just kind of go at a slope of 1/3. So if you do go to slope of 1/3 or a slope of negative third to make your V shape, then you'll end up getting that particular resulting graph right there. So those are all the elements that we want to be able to understand individually, and it turns out that we can kind of match them all together to do various transformations with an absolute value sort of graph. So what we want to be able to understand is absolute value equations of the form y equals a times the absolute value of x minus h plus k. So what I want you to take away from here is that this a and this h and this k value are really just like numbers that we should be able to plug in. So really the x and the y that are still in the black text there will just kind of remain as variables that will represent as the unknowns. So the effects of the a and h and the k you should all know. So this a, this multiplicative factor, is going to vertically either stretch or compress. And that depends on the particular value of a itself. So to kind of model that, I want to use this number line right here to represent the possible values that a could be. So it does turn out that anytime your a value is somewhere between -1 and 1, then what that does mean is then the absolute value of your a is actually going to be less than 1. And what you're going to see then is you're going to see a compression. Okay, because multiplying by some kind of smallish number like that is going to make the graph go less. Otherwise, outside of that range, if you're greater than 1 or if you are less than -1, then in either of those two cases, that's where you're going to see a vertical stretch, because the absolute value of a is actually going to be greater than 1, and whenever you multiply it by something greater than 1, it's of course going to increase the magnitude of that particular number. Otherwise, this h value right here is going to have the effect of a horizontal translation by that particular number of units. So remember that if that is a minus, it's going to shift it right. If it was a plus, then it's going to shift it to the left that many units. And then if you're adding some number outside the absolute value, that's just going to do a vertical slide of the graph up or down, so a vertical translation by k units. And that one, if it's a plus, it's going to go up. If it's minus, it's going to go down. So let's take a look at some examples where we are going to graph with all these elements in mind. So we're asked to graph each of the following equations and then also describe the transformations of each equation compared to y equals absolute value x. So in the first equation right here, it's pretty simple and pretty basic because we just have y equals absolute value of the quantity of x minus 3. So if you are adding or subtracting some number inside the absolute value with x, that's going to horizontally move the graph. So when you are subtracting a positive 3, that will move the graph right 3 units. And that's the only thing that's different about this equation compared to y equals absolute value x. So we just need to shift the graph right 3. So I'm just going to put a dot right there for where the vertex of the v will be. And then we know that it's going to go at a slope of 1 and then also a slope of -1. And then that gives a beautiful sketch of that graph. So we are also asked to describe the transformations compared to y equals absolute value x. So when we compare this to y equals absolute value x, then we can say that y equals absolute value x minus 3 is a translation 3 units right. Okay, so I wrote a lengthier little explanation there. I'll try to abbreviate a little bit more on some of these further examples right here. So in the next example, you're going to see that there is some number that's kind of multiplying in front. We're going to kind of wait on that until the very end of all of these. So what you really want to focus on first is finding where that vertex is going to be, which is really determined by anything you add or subtract inside the absolute value, as well as anything that you add or subtract outside the absolute value. So inside there's nothing going on in this particular one, but outside there's a +4. So remember that outside the absolute value is going to shift the graph vertically. When it is +4, it's going to shift it up 4. So there's only going to be a vertical shift, no horizontal shift. So we know the vertex is going to be where I made that red dot right there. Now because there's a negative, we know that's going to reflect the graph upside down, and then it will just go at a slope of -1 or 1, because it's just a negative, it's just 1, right? -1. And so that will give us the sketch of that graph of f right there. And then for the graph of g that's defined right here, you do see in this one now that actually you do have addition or subtraction both inside the absolute value with x and then outside of the absolute value quantity. So in this case, when you do have a plus inside the absolute value, that is going to shift to the left, and then of course one particular unit, because that It's a plus of 1. And then the minus outside is going to shift this down 6 units. So by going left 1 and down 6 from where the origin is, that's going to be where that's at, and that's going to be the vertex of your graph. You'll also notice that there is no value in front right there that's being multiplied. It's not 2 or half or anything like that. So that means that your v is just going to go at its normal slope of 1 and -1 and also just be facing up, just like you see there. So now we want to take a look at some translation along with a little bit of stretch or compression. So with this particular one, you're going to want to ignore the 3 and wait for that until the end, because what you'll want to figure out first of all is where am I going to start my vertex at. So we're going to have to move left 8 and down 2 accordingly, because we have plus on the inside, which tells us to go left, and minus on the outside, which tells us to go down. So if I do go left 8 and down 2, that's going to be the new location of our vertex. Now that 3 is going to tell us we're going to stretch by a factor of 3. It is positive, so the v is still going to face upwards. So it's really just kind of like going at a slope of 3. So going that way, and then just going the other direction, really kind of at a -3 slope in that direction. And that gives you the completed graph that we see right there. And then for this example right here, you can see that we've got a minus, which tells you to go right, and then a plus, which tells you to go up. So right 3 and up 3 lands us right there for a vertex, so always do that first. And then the last thing you want to do is any stretching, compressing, and reflecting, which is always that multiplicative factor. It's negative, so we know this is going to flip upside down, and then also it's a 2, which is going to stretch it by a factor of 2. So really just go kind of a slope of 2, but just go upside down, just like I'm making these dots right here, and then that's good enough, and draw your arrows, and then you're good. And then one last one, this one's going to have a compression because it's multiplied by that 1/4, which is less than 1. Before we do so, though, you're going to see that we are going to move right, because you have a minus on the inside with the x, right 1 unit, but there is no adding or subtracting of any value out there, so you don't need to move up or down. So it's just a rightward shift of 1 unit. That's going to be where the vertex is, that blue dot. It's negative, so it's going to go upside down, but then you'll go at like a slope of 1/4. So this definitely compresses the graph, makes it much flatter, kind of sort of like a pancake, and that gives you that completed graph right there. So I do need to kind of just back up just a little bit and go through some of the transformations, because we do need to describe the transformations that happen with each of these. So if I do back up just to the previous page, just real briefly right here. So if I go to that middle one that's in the red color right there, you can see that the +4 shifted the graph up, but then we also reflected upside down. So just kind of bullet pointing this, I'll say that we did translate up 4 units, and then we also did reflect in the x-axis because of that negative. Okay. In the next example, we did translate some units, so we ended up translating left 1 and down 6. That's good enough to abbreviate what happened in that one. And then for these 3 examples that we did just most recently, so starting with this first one, we did translate left 8 and down 2. And then we also did stretch. And when you say stretch, you have to specify that it's a vertical stretch, because there is such thing as a horizontal stretch. We're not going to talk about that sort of stuff yet. So we stretch vertically by a factor of 3 in that particular case. I guess I don't need that third bullet point there. The next one, I can have probably 3 bullet points, because we did translate, in this case, right 3 and up 3. And then we also did do a vertical stretch by a factor of 2. And then that negative that we multiplied by does tell us that we did do also reflection in the x-axis, that it flipped it upside down to go across the x-axis. And then finally, for the very last one, this one actually did have a vertical compression, because 1/4 is smaller than 1, so it's a vertical compression by a factor of 1/4. And then the negative also tells us that we did also do a reflection in the x-axis, and then there was just a 1 unit translation to the direction of right. Yeah, so 1 unit translation to the right.